Word problem number 4 is another exponential growth problem. As soon as you see the term half-life, you should be thinking, hey, that's a PERT function. I don't know what we're going to do with it, but I might as well write it out right away. P of t equals PERT. Pe to the RT, and if you want to write it as P naught to make it more accurate, because that's your starting population, you can. But I just remember that P is starting population. And in this case, it's not a population, it's how much cobalt-60 we have, but it's the same question. It says cobalt-60 has a half-life of 5.24 years. So what they're telling us is you will have 1/2 of the original amount of 1, because it's 100% of e to the r times 5.24 years. So we can already use this to find r. We don't even need to look at what they're asking for a and b, because that's what they're going to be using it for. That's why they gave us that information in the question. So I can immediately remember, I hope you remember, if you have a variable in your exponent, that's a natural log. Natural log solves that issue for you. So we can write ln of 1/2 is equal to ln of e to the 5.24r. And when you have a natural log, the exponent can come out of the natural log and become a coefficient like this. Isn't that better? Isn't that better? So we can say ln of 1/2 is equal to 5.24r ln of e. And wouldn't you know it, the natural log of e is 1. So that's just gone. And if I divide by 5.24 here, I'm going to get r equals, let's put it right in the calculator machine together, natural log of 1/2 divided by 5.24. I get negative 0.1323-ish. And I'm going to save that for later. And now we can bother to look at what they're going to ask us. Find the mass that remains, so that is find P of t from a 100 milligram sample after 20 years. So here's our t. And that's going to equal our starting population of 100, or in this case, starting mass of 100, but it's all the same to the equation. E to the r, which we've already found because we're awesome together, and that would be 20 years. I got about 7.07 milligrams remaining. And if there's a decimal error or something, it's because I rounded on this rate to only 4 digits. So make sure you use the full thing. But that's pretty close. It's pretty close. You should get full credit for that. Now for part B, it says how long would it take for the mass to decay to 1 milligram? That means we already know the result, and we know the starting mass, and we know it's e to the negative 0.1323. The only thing we don't know is how much time there is. Well, we have a variable in the exponent. It's the same thing as we doing before. We're going to be doing natural log. Let's divide this 100 away first and just make that a 0.01. And then we'll take the natural log of everything. So forgive me if I do two things in one step, but I'm sure you can follow it. Equals negative 0.1323t ln of e. Again, just brought that out of the natural log, didn't we? You did this a couple times in this problem alone, I think. So let's cross the ln of e out, because that's just 1. And let's divide by this, and I'm going to get t equals ln of 0.01 divided by negative 0.1323. That should compute to about 34.8 years. That should be full credit for that problem. So the trick here, really, this isn't even calculus as far as I'm concerned, but it leads into it, is the PERT function. This is algebra 2 more than anything, but I find almost all of my calculus students fail because of algebra, not because of calculus. So take this with you into the next word problem.